Hi everyone, I'm Oldfield and I'm a fourth year civil engineering student at Waikato University, and this is my research and development project for this year. From a literature review that I conducted earlier in the year, I discovered that there is a need for a more sustainable use of tyres, which has led to the following investigation. Within this study, I've investigated the properties of concrete mixes with rubber waste in New Zealand, or more informally known as rubberized concrete. As you may be aware, there is no end-of-life cycle use for tyres currently, and with New Zealand generating around 4.7 million tyres for waste each year, this is becoming a significant problem. The New Zealand government has recently announced that tyres are becoming a product of stewardship. This means that for whoever designs, produces, sells, or uses this product, they must take responsibility for minimising the product's environmental impact throughout all stages of the product's life. This is what has created the driving force behind this investigation, as I want to help with the global sustainability where possible. By recycling tyres and using them in concrete as a partial cement or aggregate replacement, a significant reduction in carbon dioxide and also the Earth's natural resources can be achieved. With this in mind, the main aim of this research investigation was to determine the effects that recycled rubber had on the different fresh and mechanical properties of concrete, and to try and create a more sustainable use for this type of waste. This study aims to discover a waste rubber concrete composition that can be used in large-scale construction applications within New Zealand and ultimately all over the world. For this study, the experimental program was primarily based around the substitution of natural aggregates. Two different concrete mixes were designed under the ASTM standards to test the effect of replacing coarse or fine natural aggregate in concrete with different sized waste rubber. In concrete mix 1, GAP 7 aggregate was replaced by 7mm rubber arena mix, and in mix 2, sand was replaced by various proportions of rubber powder, 0.8 to 2mm chip, and also 2 to 4mm rubber chip as shown in these figures here. These proportions were based on the particle size distributions obtained by the sieve analysis of the sand. Each mix was designed with a control sample, meaning there was no waste rubber present, and then a 5%, 10%, and 20% replacement of natural aggregate by weight, and these molds were then cured for 7 and 28-day testing. As shown here, the slump of concrete mix 2 increased considerably, meaning it was a lot more workable with more rubber, while concrete mix 1 showed a similar effect, but less significant due to the larger rubber particles. The destructive tests, which are the compressive and splitting tensile strength tests, were impacted quite significantly from the addition of waste rubber. It was discovered that the fine aggregate replacement had less effect on the strength than the larger rubber aggregates, although beyond 10% replacement, we can see quite a decrease in compressive strength by approximately 60% in each mix. The last graph on the left displays the splitting tensile strength results for mix 2, and it can be seen that the addition of rubber up to 10% has minimal effect on the splitting tensile strength of concrete, which is a desired result. The water absorption results for both mixes show a slow initial water absorption. However, beyond 6 hours and through the secondary stage until 6 days, the water absorption increases with the addition of waste rubber. Overall, this study found that waste rubber in concrete has significant effects on both the fresh and mechanical properties of concrete, but based on literature, rubberized concrete can present some favourable properties in concrete, and therefore further research is required within the study to discover a suitable use for rubberized concrete in New Zealand. I would like to take this time to acknowledge Mostafa, who has been my project supervisor for the course of this study. Thank you for your continuous guidance and encouragement. Your support is greatly appreciated. I would also like to acknowledge Richard from Treadlight, who has generously supplied the waste rubber for my research. Thank you for showing me around your plant and assisting me with finding the required material. Lastly, thanks to Liam Baker and Cole Dawson for their help and cooperation within the lab and making this project achievable through the tough times of COVID-19. Thanks.